chapter 3 is where we are currently headed. Atomic structure. Whoa, got a little carried away with my R's there. Atomic structure. This is material. You all got periodic tables last week, right? Last Friday?
Yes.
How's the studying for the quizzes going, by the way?
I didn't do it until today.
Okay, there's 2 of them that you can definitely already start studying for. One of them obviously is the element quiz, because you have all the information you need for that, symbols, names, boom, easy. The other one that, remember I kind of made the little joke about you should have started studying 3 days before I actually introduced the quiz. Did I make that little joke?
I don't know.
No.
Okay, the polyatomic ion quiz, did I mention the polyatomic ion quiz?
Yes.
The stuff on the back? Okay, you should have started studying that 3 days before you knew that it existed. So when I described that to you Wednesday or Friday, you should have started studying for that Tuesday prior to that. I know that doesn't make any sense, but you note the urgency that I'm trying to instill in you. That one's hard, people. That one's hard. I would study for that one at the same time that I'm studying for the element quiz. Now, that ion quiz is going to happen in the monatomic ion quiz, is going to happen in the middle. That one, over the course of the next couple of days, we're going to learn about that. It's very similar to the element quiz. We're just adding a little bit of information to it, the charges on the ions and everything. Over the next few days, we'll learn how to do that. So you'll also have at least a week to prepare for that one too. Okay? But I'm telling you right now, by far, the hardest one is that polyatomic ion quiz. I mean, by far. You thought the conversion quizzes were hard. Okay? So anyway, moving on. Atomic structure. This is all material. I am anticipating getting through this material fairly quickly. This is most of this you've had before in physical science, okay? So we're going to zip through the stuff you've had, add a few little things here and there that you probably weren't exposed to, and then get out of here so we can go on and do some other things. Before I do this, before I go into the detail, I want to remind you, have you guys ever heard of the Bohr model of the atom? Has that phrase ever come up before? Which is really about the only model of an atom you've ever probably known, and that's where you have this. Oh, I forgot to do something in my other period. And this. Now, we're going to talk about the actual arrangement of these things and the relative size of these things, but does anyone recall what this piece in the middle is called? It is the nucleus. And now the rest of this area, the areas here, and I don't want to use that color, let's go with this. These areas here, you may have been taught a number of different words here. In general, we're going to call the area that's not the nucleus the electron cloud, just to be the general area. However, what about the detailed pieces of this? These are the words that you guys may have heard before. Anyone remember what these areas have any idea? What's that? Oh, well, that would only be valence what? Ah, no, not yet. Okay, have you used the words energy levels yet? Has that come up? Energy levels? No? Okay. How about orbitals? Has that come up? No. How about shells? Okay. Anyway, these three, for the time being, are relatively interchangeable. We'll get more detail and fix that later. In general, all that entire area that's not the nucleus is called the electron cloud. I do want to talk about this nucleus. So does anyone remember what's in the nucleus? Protons and neutrons. Okay. I'm going to actually use the two symbols that we're going to use for proton and neutron, a capital P with a plus sign and a capital N with a 0. Here's the one thing that I forgot to mention in my other two classes. Where else have you guys come across the word nucleus? In what other science class? Biology, right? The nuclear cell, or the cell nucleus, right? Here's the difference. In biology, there's actually a structure that surrounds the nucleus, the nuclear membrane, right? You guys are familiar with this. In an atom, there is no structure. Okay? I just want to emphasize that because I think a lot of students carry that whole structure part from biology over to chemistry and think that there's actually a structure that hangs, that keeps everything together. There is no structure. To answer Ashley's question, we will get into that later, probably tomorrow. You're asking what does hold it together, right? Okay, we're going to get to that tomorrow. There's a thing we're going to do about that, okay? But for right now, we're not. All right, moving on. Relative size. Here's an interesting analogy. You've probably heard this before, very similar analogies before. It's very difficult to draw an atom to scale, both the nucleus versus the rest of the atom, because the nucleus is such a small part. Has anyone ever been to Ohio Stadium or Buckeyes play? Or you've seen picture or television, whatever. Very, very, or driven by, very, very large place. Do you guys agree? Very, very large place. All right, so if the nucleus of an atom were about the size of, say, a baseball or maybe even a ping pong ball or something, a really small ball, okay? The first energy level would be on the outside of the stadium. The nucleus would be the baseball. The first energy level would be on the outside of the stadium. That's not to scale, is it?
Yeah, no.
So my question to you is, what's in between the nucleus, the baseball, and the outside of the stadium? And that's precisely it, nothing. So atoms are made up of mostly nothing. It's a fun thing to contemplate, isn't it? Nothing. Some of you are really good at it. Moving on. Just a little joke, just playing. All right, so let me see. Let's go into a little bit more detail on those subatomic particles. Okay, which are the particles that make up an atom. We just talked about them in no particular order. We're going to look at protons, neutrons, and electrons. Whoa. Okay. Obviously, we already talked about where protons are found. They are located in the nucleus. What other bit of information do we know about a proton? It's positively charged. And I know you've been exposed to this material. It's possible you were not exposed to this material. It has an actual mass of 1.67 times 10 to the negative 24th grams. Now I left a little space here. You're going to find out why in a little bit, why I left a little space here. If you could just leave a smidge amount of space there too, that'd be lovely. Now I asked my other class, I said, would you guys want this expressed in grams or kilograms? Which do you have a better sense of, a gram or a kilogram? And of course everybody says, oh, gram. I said, okay, how many grams is this book? And they all sat there basically like you guys are sitting there right now going, I don't know. Okay? So as it turns out, you don't have much of a sense of either gram or kilogram, do you? Maybe you do. What's a kilogram equivalent to? See if anybody remembers this. in a US system of measurement? A little over 2 pounds. Does anyone remember that? 2.2 to 5 pounds
Yes.
per kilogram? So that's about a kilogram-ish, give or take. Still not much of a sense there, huh? All right, does anyone have a nickel with them? Okay. I have a nickel somewhere. I had one last grade. Unless somebody stole it, I still have it. Now, this is a coincidence. Has nothing to do with the amount of money that it represents. But a nickel has a mass of about 5 grams. Is that a perspective that you can deal with? A little bit more, okay, so anyway. Of course, when you get out to this, it really doesn't matter, does it?
Yeah, no.
Okay, anyway, moving on. Now, is this new to you? Is that the first time you've been presented this information? Okay, there's a significance of that here in a second. And then it has a relative mass of 1 AMU. So that means compared to the other particles in the nucleus, we're going to say it has a mass of 1. Does anyone know what AMU stands for? I'll give you a hint. It's not a little bird that you find in New Zealand. That would be an emu. This is an AMU. Atomic mass unit. Okay. All right. On to the neutron. Also, as we know, located in the nucleus. What's the charge on a neutron?
Zero.
Yeah, no charge. No charge or neutral. An actual mass of 1.67, I'm leaving a small space, times 10 to the negative 24th grams. What's interesting about that?
The same.
Same as what? The proton. Therefore, it has a relative mass, anyone want to take a stab? Of 1 AMU. So essentially, as far as you need to know, for this class, the mass of the proton and the mass of the neutron are the same. Although I am going to provide some information for you here so we can have another little discussion. And then lastly, an electron, as we know, is located in the electron cloud, negatively charged, as you know. Actual mass of 9.11 times 10 to the negative 28th grams. What can we say about the mass of the electron compared to the mass of the proton or neutron? What's that?
Smaller.
Quite a bit smaller. We're talking 4 orders of magnitude, 10 to the negative 28th, 10 to the negative 24th. We're approaching somewhere between 1,000 and then 10,000 times smaller than a proton or a neutron. That's pretty darn small, right? Therefore, since it's so small relative to those things, we're going to say it has a relative mass of 0 AMUs. So that would be like the analogy that I had used earlier this year when I forget whose hair it was I was pulling off. It was probably Mariah's. Was that you? Where I was acting like I was going to pull a hair off of your head? You have no idea what I'm talking about. The rest of you guys may remember this. Okay, if I was going to pull a hair off of Ashley's head, how would decrease, but if she was standing on a vacuum scale, would we ever know?
No.
No, because there's just not enough mass there to be detected by the scale. Does that make any sense? Okay. So that's why we say even though it does have a mass relative to the other particles, it has very, very little, essentially zero mass. As it turns out, when we start looking at the numbers on the periodic table, those average atomic masses don't include the electrons because at that level of precision, they're not detectable. Anyway, moving on. Now, I do want to have a small discussion about why I left these little spaces here. This next bit of information you are not going to be tested on, you are not going to be quizzed on, you do not need to remember for this class. However, it's possible that some of you guys go on and do some other things that you don't even know that you're going to do, because if you told me I was going to be a teacher when I was your age, I would have laughed at you. If you would have told me I was going to be teaching chemistry, I may have hit you, because I hated chemistry, much like some of you do currently.
So why do you currently work?
You never know what you're going to end up doing. Okay? You never know. You're going to change 4 times anyway. So, anyway, where I'm going with this is, some of you might move on and find the information I'm about to talk about be interesting and or apply to what you're going to do. As it turns out, if I go beyond 3 significant figures, the mass of a proton is 1.67242. You don't have to write this down, just go with it, okay? You can if you want, but you don't have to. The mass of a neutron is 1.67493 AMUs. So slightly bigger. You guys following? Okay, slightly bigger. Why? Well, it has something to do with what a neutron actually is. Before I go there, I'm going to talk about this topic that you may have been introduced to at some point in time in physical science or something else. Did you guys ever get into radiational, nuclear decay, nuclear radiation at all? Was that ever mentioned in your physical science classes?
We talk about waves, I mean, it's about...
Okay, that's fine, that's all right. You guys are aware of the fact that nuclear radiation or radiation occurs, okay, radioactive particles, okay, and you may have heard of nuclear decay. Did you guys do anything with carbon dating or anything like that?
Yeah.
Biology, possibly? Okay. This is where all this comes from. Well, there's 3 main, again, you don't have to write this down if you don't want. There are 3 main types of radioactive decay, or radioactive, decay. Alpha, beta, and gamma. Now, I don't know if you guys know much about the Greek alphabet or not. Those are the first 3 letters. You may have been aware of that, okay? So when they discovered these particles or these phenomena, the only reason they called them this is because the alpha was discovered first, beta was discovered second, gamma was discovered third. They didn't know what else to call them, so they called them alpha, beta, and gamma. Turns out an alpha particle is a helium nucleus. Now, what's in helium? By the way, I forgot to mention this to you because this is the first time all year that this has happened. From this point forward, there aren't very many days that we are going to have in this class where you're not going to be needing to refer to a periodic table. So, if you already don't have a periodic table out, why don't you guys go ahead and get that out. The reason I'm asking this is, what's in a helium nucleus? Well, we all know that helium has an atomic number of 2. Maybe we don't know that. Which means it has 2 protons. Its average atomic mass is 4, which means that it also has 2 neutrons. So a helium nucleus has 2 protons, 2 neutrons. Okay? So what's the charge on a helium nucleus? Positive. It's the only particle that's in there that has a charge, right? So that's why they were able to discover it relatively quickly. It's the most massive of the 2, and it's also got positive charge. So it's relatively easily detected. The beta particle is essentially an electron. That's all it is. So let's go back to the alpha thing. If an atom undergoes alpha decay, that means it loses out of its nucleus a helium nucleus, meaning that it loses 2 protons and 2 neutrons. If it loses 2 protons, it's now a different element. Does that make any sense? It lost 2 protons. If an atom undergoes beta decay, it loses an electron. Now, you guys learned way back whenever it was in physical science that if the number of electrons changes, that makes it an ion, right? Which is a charged atom. But this electron that I'm referring to does not come from the electron cloud. It comes from a different location that also creates a different element. And you're sitting here thinking to yourself, well, the electrons have nothing to do with what element it is, and that would be correct. So now you have to understand what a beta particle is and where it comes from. It is an electron that comes from a neutron. So really what a neutron is the combination of a proton and an electron. Okay, what's the charge on a proton? Positive. What's the charge on an electron? Negative. They cancel each other out. You put the 2 together, what's your charge? 0. That's the neutron. Also notice that the neutron is slightly, very slightly more massive than the proton, right? Why? It's got an electron in it. Does that make any sense? So, when a species undergoes beta decay, okay, one of the neutrons breaks apart into a proton and an electron. That electron leaves the atom, the proton stays in the nucleus, and now we have a different element with 1 more proton in it. So either way, you're getting some different elements out of this. Now, turns out a gamma, and I should say this, it's not a particle, it's a gamma ray. So all gamma is energy. The gamma ray is energy. And when either of these 2 processes occur, you're also going to get the release of some energy, so energy will also go away. We'll talk more about where that energy comes from a little bit tomorrow, as it turns out. Anyway, this is all just stuff that I'd throw at you because some of you, like I said, either are interested in this stuff and or may end up doing something with it later in your life. Any questions so far? Okay. Next, how all this relates to the periodic table. You guys have probably done this before. I know when I taught physical science, I'm giving you exactly the same lecture I used to give my freshmen. I just never added the others, the beta, alpha, beta, delta, all that kind of stuff. Let's talk about chlorine. Now, I'm going to put stuff up here representing a block in the periodic table that may or may not match where your stuff is, may or may not match what's up here. Who knows? It doesn't matter. Different periodic tables put things in different places. Let's go. And let's go with this. Okay, so anyway, that's the main information that might be located on the periodic table. Obvious, well, maybe not obviously. Anyone recognize what the 17 represents? This is called the atomic number. Does anyone recall what the atomic number indicates? Number of protons. Really, essentially, that's what it is. The atomic number is the number of protons. However, if the atom is neutral, meaning it doesn't have a charge, that means it has the same number of electrons as it has protons, it also tells us the number of electrons. You kind of used that idea before? Okay. Now, I do want to bring this up. If it has different numbers of electrons, then that's called an ion. And we, as a class, when you speak to each other and you amongst yourselves, are really gonna start being careful about calling things atoms versus calling things ions. Atoms don't have a charge, ions have a charge. So I use those two words in specific ways. I just want you guys to be familiar with that. Yes, Mariah?
Is there a reason that you put 35.4?
There is, oh, no, it's 453. My bad, got ahead of myself.
It just says 4.5.
That's okay.
It says 4.
That's okay. We'll go with it. As you guys can imagine, this is the symbol. We're done talking about that. Oh, other than the fact that all of the symbols, like we talked about before, always start with a capital letter. If there's any subsequent letters, they're always lowercase. Okay, done with that. As you guys can surmise, this is the name, which leads us to this, which is the average atomic mass. And that's what I want to spend a little bit of time talking about, because that's going to lead us to a number of different places. As it turns out, there is not a single chlorine atom in the universe that has a mass of 35.453. Not a single one. We'll talk about that here in a little bit, why that's true. Okay? Average atomic mass, the definition of that is, it's a weighted average of the isotope, the mass numbers of the isotopes. Hey, how's it going? Of an atom. Weighted average of the mass numbers of the isotopes of an atom. Are there any words up there that look unfamiliar in that definition? Okay, there's probably at least two, if not three, but nobody's willing to admit that. What's a weighted average? Not average weight. Okay, well, as it turns out, you're all very familiar with what weighted averages are. You just maybe forgot. That is how your grade is determined in this class. Does every component contribute equally to your grade in this class? No, what component contributes the most? Tests, 50%. What's the next most? Labs, 25. You see where I'm going with this? Each component has a different weight or contributes different amounts to your overall grade. So many of your classes use a weighted average probably. Do any of your classes use a straight or arithmetic average where you just add up all the points and divide that into how many you earned? Is anybody still doing that at all in some of your classes? Not very many of your classes, I don't think, are doing that anymore. I know Homan does that, but I don't think any of the rest of you do. All right, so a weighted average, each component contributes a different amount to the overall average, okay? Mass number. I like to start this discussion off by asking you, where on the periodic table will you find the mass number? Well, don't look too hard because you're not going to find it. It's not on there. None of the mass numbers are on there. So, well, they're included in this, but we'll get to that here in a second. So what's a mass number then? Whoa. It indicates the number of particles in the nucleus. The number of particles in the nucleus. So what are the particles in the nucleus? Protons and neutrons. So in other words, this is number of protons and neutrons. Okay, the mass number refers only to the number of protons and neutrons. What's the mass of a proton? Anyone can shout this out. Evan? Anyone, Evan, can shout this out. What's the mass of a proton? 1. Excellent. Jenna, what's the mass of a neutron? 1. So if we know the number of protons and we know the number of neutrons, we also know the mass of the nucleus. Would you agree? Okay? Remember, we already talked about how electrons really don't contribute significantly to the mass of the atom because they're so much smaller. Okay, that's going to become important here in a little bit. And then finally, what is an isotope? You guys probably remembered studying isotopes before? Possibly. Okay? Isotopes are, and it's easier for me to define them in the plural, atoms of the same element with different mass numbers. Atoms of the same element with different mass numbers. That has all kinds of implications, that statement right there. You guys notice this, you've read in the science books, they're written very densely, meaning every sentence, nearly every word means something. It's not like an English book where they use all this, adjectives and adverbs and all that stuff, okay? Every word means something. So atoms of the same element, which of the particles does that give us information about? Atoms of the same element. Which particle is going to be the same for all of those atoms? That would be the number of protons, the atomic number, right? So all of these isotopes are going to have the same number of protons, but they're going to have different mass numbers. And we just got done saying that the mass number is the number of particles in the nucleus, which is protons and neutrons. Therefore, what's another way of saying what an isotope is? Atoms of the same element with different numbers of neutrons. Okay? There's a couple of different ways that we can write out the symbols for isotopes. I'm going to show you both of those. I would do this below, but I'm starting to run out of room, and some of you guys wouldn't be able to see it, right, Nick? And so I'm going to move it up here. You guys following? Okay. A couple of different ways to do this. Since we started on chlorine, I'm going to continue with chlorine. Here's one way to write this. There are 2 different isotopes for chlorine. Okay? Remember I said earlier that there's not a single atom of chlorine that has a mass of 35.453? Didn't I start that off with that? The only 2 masses you're ever going to find are either a 35 or a 37. Okay? So now, this then obviously is the mass number. So that information is going to have to be provided for you one way or the other. The mass numbers are going to have to be provided for you, or enough information to find them. Okay? This down here, as you know, is the atomic number. Now, mass number is, as we said, protons and neutrons. Atomic number is number of protons, right? So how can I find the neutrons? Very simply So the number of neutrons, you just subtract. Was it third grade that you learned how to line numbers up like that and subtract? Okay, so we have 18 neutrons. Over here, we have 37 protons and neutrons. Once again, 17 protons, still chlorine. So how many neutrons? 20. So, once again, atoms of the same element, chlorine, with different numbers of neutrons. Okay? Is this familiar? Did you guys cover this before in a previous class? Some of you, maybe you did, some of you don't remember. Okay, moving on. There's another way that we're going to symbolize these. I'm going to go ahead and get rid of this. This is one way of writing out the symbols. Another way is by writing it like this. Either the name or the symbol, it doesn't matter. Okay. You can either write the name chlorine -35 or you can write the symbol -35. Doesn't matter, it still means the same thing. This is assuming that you have a periodic table available to you, because you have to know that chlorine has an atomic number of 17, okay? So you actually have to know a little bit more for this one. You guys have probably seen these before. Have these been introduced to you? Maybe? Okay. Moving on. What do I want to do next? That was a lot of information so far. How much time do I have?
About 5 minutes.
Okay. That kind of gives me a clue as to where I want to go next. Earlier, I had said that there's not a single chlorine atom that has a mass of 35.453. Right? It's either going to be chlorine 35 or chlorine 37. If Ashley went to Australia and grabbed some chlorine, which I would highly recommend not doing because chlorine is a poisonous gas, but still, let's imagine that she did, not a single one of them would be chlorine 35 or would have a mass of 35.453. Let's say Alex went to Mars, grabbed some chlorine. Once again, both things are kind of interesting, but guess what? Not a single atom would have a mass of 35.453 because that is a weighted average. Each of these components is contributing a certain amount. You're my class. It just occurred to me. My second period class has 5 boys in it. I didn't even recognize that until Holman said something when the kids came in today. I said, oh my gosh, there's no boys in this class. I never even looked at it. And now that I'm looking at your class, I'm sitting there thinking, there's no girls in here. There's 8 girls in here. That's it. Wow, interesting. Okay. So, where do I want to go? Did we talk about who discovered all the particles or when they were discovered?
Yeah.
Let's do that real quick and then we'll be done with this. This is not something you're going to be tested on. This is just more for historical kind of information. Believe it or not, the electron was the first particle to get discovered. This happened in the late 1890s, like 1896, 1897, and so on and so forth. The actual flow of electrons had been, they knew something was flowing, they didn't know what it was. Electricity, you guys are aware of electricity, right? That is flowing electrons. Well, they didn't actually discover what was flowing until, like I said, the late 1890s. A guy by the name of J.J. Thomson did some experiments, figured this out. Figured out that they were negatively charged and that they were individual particles. It was about 10, 15 years after that, the early 1900s, 1910-ish or so, that someone finally devised a way to discover the proton. Now, both of those particles were relatively easy to discover because they have a charge. Okay? It wasn't until like the mid-1930s, nearly 20 some odd years later, that finally someone discovered the neutron. What do you think took so long?
You need to find it.
There's no charge. They were aware of the mass, There's something there. They just didn't know what it was, okay? And they finally isolated with the thing called the neutron, which, as it turns out, opened up a whole can of worms called, well, the atomic energy type thing, and which led to atomic bombs. That whole discovery of the neutron just kind of opened everything up. Again, so that was like the 1930s or so. I just thought that was kind of interesting. Of all those particles, only one guy won the Nobel Prize, and that was the guy, his name was Chadwick, that English guy that discovered the neutron. So, interesting little thing there. When we get into chapter 4, which for you guys won't be until after Christmas, we'll talk about that in a minute. We're going to talk about how Einstein only won one Nobel Prize, and it wasn't for what you guys think it was. What do you guys, what's Einstein famous for?
Light bulb.
Not the light bulb. E equals MC squared theory of relativity.
I
Yeah, he
know
never.
what it is.
Whew. That would be Edison. Starts with an E.
I hate myself.
Anyway. This,
This,
I just wanted, because some of you guys might know some of the kids that I have in honors chemistry, right? After chapter 3, we're going to split. Okay? Mainly for my sanity. Meaning that if I kept teaching the same chapters with all of my classes, I go crazy at the end of the day. I flat out go crazy. I'm teaching the same thing for the 4th and 5th time. Okay? So after this chapter, you guys are going to go to chapter 7 and 8 and 9. Then we're going to come back and pick up 4, 5, and 6. Those guys, we're just going to keep on going 4, 5, 6, 7, 8, 9. And the only reason I'm doing that is to keep me sane. Because otherwise, I lose it. You should see me at the end of the day. This is the 3rd time I've done this today already. I'm already starting to lose it. Well, that, in fact, in Mariah's. But still. Just kidding, Mariah.
I didn't hear you.
Oh, I know, because you had your headphones in.
we didn't try